Chapter 1, Solid State Part 3. 1. Packing of particles in crystal lattice.
2. Close-packed structures. One-dimension close packing. Two-dimension close packing. Square close packing. Hexagonal close packing.
3. Three-dimension close packing. 4. Packing efficiency. Simple cubic. Face-centered. 5. Number of particles and unit cells in xg of metallic crystal.
Packing of particles in crystal lattice.
Packing of particles in crystal lattice. While describing the packing of particles in a crystal, the individual particles are treated as hard spheres. Constituent particles of a crystalline solid are close-packed. The closeness of particles maximize the interparticle attractions. What is coordination number? The number of neighboring spheres that touch any given sphere is its coordination number. Here orange sphere is surrounded by neighboring 4 green sphere. Therefore coordination number of orange sphere is 4. In second diagram 1 orange sphere is surrounded by 8 yellow sphere. Therefore coordination number of orange sphere is 8. Magnitude of the coordination number is 8. Measure of compactness of spheres in close-packed structures.
The larger the coordination number, the closer are the spheres to each other. Here in this coordination number 8 is greater as compared to coordination number 4. So arrangement having coordination number 8 is compactly arranged.
The three-dimensional mode of packing can be easily explained by dividing the whole process into 3 steps. Packing in 1 dimension, 2. Packing in 2 dimension, 3. Packing in 3 dimension. Today topic, close packing in 1 dimension.
A close-packed one-dimensional structure is formed when spheres are arranged in a straight line, so that each sphere touches its neighboring sphere. Since one sphere touches 2 neighboring sphere, hence coordination number in one-dimensional close packing is 2.
Close-packed structure in 1 dimension. Consider this sphere arranged in such a way that one sphere touches the another sphere in a straight line. So, if I say what is the coordination number of this sphere? What is the meaning of coordination number? One sphere touching how many spheres? So if you can see here one sphere is touching the 2 other spheres. Therefore the coordination number of this atom is 2. Therefore the coordination number in 1 dimension is 2.
Close packing in 2 dimensions. In this topic, you study 2 types of packing: square close packing and hexagonal close packing.
Square close packing in 2 dimension. Now let's study square close packing in 2 dimension.
Square close packing. Consider first row spheres in 1 dimension, and second row spheres are stacked over each other in such a way that the spheres align vertically and horizontally. If the first row is labeled as a type, since the second row arrangement is same as first row, the second row is also labeled as a type. If we keep on placing row one above other, such type of arrangement is called a type 2-dimensional arrangement. In this arrangement, every sphere touches 4 neighboring spheres. Hence, 2-dimensional coordination number here is 4. A square is obtained by joining the centers of these 4 closest neighbors' sphere. Therefore, this 2-dimensional close packing is called square close packing in 2 dimension.
Square close packing in 2 dimension. This is the 1 dimension sphere along the x-axis. If I go on, this is the first row, another row, that is second row, in such a way that the crest of the second row is just touching the crest of the first row, and this crest are meeting, this crest and this crest are meeting, this crest and this crest meeting. Okay, so if you see the first row arrangement and second row arrangement, both are same. Label the first row as A layer, then I will consider the second row as A layer because the arrangement both are same. And if I place the third row, same thing here also, I am placing the crest of the third row is placed over the crest of the second row. If I arrange this also, it will be similar to first and the second arrangement. So first row arrangement, second row arrangement and third row arrangement, all arrangement are same. Therefore I will label the first row, second row and third row, all will be labeled as A. Therefore such type of packing is known as A type of packing. Now if I say what is the coordination number, this atom is touching the 4 atoms, 1, 2, 3, 4. Therefore the coordination number in square close packing is 4.
Hexagonal close packing in 2 dimension.
Two, hexagonal close packing. Close-packed one-dimensional row shows that there are depressions between the neighboring spheres. Now if the second row is arranged in such a way that its spheres fit in the depressions of the first row, a staggered arrangement results. If the first row is called a type row, the second row, being different, is called B type. Placing the third row in staggered manner in contact with the second row gives rise to an arrangement in which the spheres in the third row are aligned with the spheres in the first row. Hence the third row is type. Similarly, when the spheres in the fourth row is placed on third row, then the fourth row will be aligned with the spheres in the second row, and hence the fourth row would be B type. The resulting two-dimensional arrangement is ABAB type. In this arrangement each sphere touches 6 closest neighbors. Thus, the two-dimensional coordination number in this packing is 6.
Hexagonal close packing in 2 dimension. Now this is the first row. I place the second row. You can see here I have placed this sphere in between these two spheres. So if you see the arrangement of these two, first row arrangement and second row arrangement, both the arrangement is different. It is not same. So if I label this as A layer, then the second row is not matching with this first row arrangement. Therefore I will label it as B. Now when I place the third row, similar here also you can see this sphere is placed on the depression of the two sphere. This also. If I place this third row, if I see this is not matching with the second row, but it is matching with the first row. See, straight line. Okay, so arrangement is same as the third row arrangement. Therefore I will label the third row as A layer. If I place the fourth row, so how I will place the fourth row? In between this. Okay, if you see this, it is matching with the second row. This is matching with the second row, this matching. So now the second row and the fourth row are arrangement is same. Therefore I will label this fourth row as B. So such type of packing is known as AB type of arrangement. Now what is the coordination number of this hexagonal close packing structure? Now you can see this atom is touching how many atoms? Just see, this atom is touching 1, 2, 3, 4, 5 and 6. Therefore the coordination number of this atom is 6, or you can say coordination number in hexagonal close packing structure is 6.
Today we examine close packing in 3 dimensions. As demonstrated by this configuration, the most efficient use of
Simple cubic structure in 3 dimension. To explain 3-dimensional simple cubic structure, square close-packed layers are stacked one over other. Now square close packing in 2 dimension is placed horizontally, and it is first layer for 3 dimension. Here, the second layer is placed over the first layer, so as to have its spheres exactly above those of the first layer. In this arrangement, both first layer and second layer are both aligned horizontally and vertically. Thus subsequent square close-packed layers are placed one above the other in the same manner. Since all the layers are alike, and are labeled as A layers, this arrangement of layers is described as AAAA type. It can be seen that in the simple cubic structure, each sphere touches 6 neighboring spheres, 4 in its same layer, 1 in the layer above and 1 in the layer below that sphere. Hence, coordination number of each sphere is 6. Structure that results on stacking square close-packed layers is simple cubic. Its unit cell is the primitive cubic unit cell.
Will take this square close packing and I will place it horizontally. Now this is the first layer of in 3 dimension. Now I will place another square close packing and I just place exactly above the first layer. Now I will place the third layer. Similar, it is also a square close packing in 2 dimension. I am placing it exactly above the second layer, and if you see here, second layer is exactly above the first layer, third layer is just exactly above the second layer. So all the layers are same. So if I assume the first layer as A layer, then second layer will be assumed as A layer and third is also assumed as A layer. So this type of arrangement is known as AA type of arrangement. In this, if you can see here, if I remove this part, cube part, 1, 2, 3, 4, 5, 6, 7 and 8 below. So this is a, if I remove this part, it will be primitive cubic cell. Primitive cubic cell is what? There are 8 atoms or 8 constant particles at the 8 corner of the cube. So similarly here also 1, 2, 3, 4, 5, 6 and backside 7 and 8.
Polonium is the only metal that crystallizes in simple cubic closed packed structure.
Hexagonal close packed HCP. ABAB type close packing structure.
2. Hexagonal close packing. ABAB type in 3 dimension. Let us consider a 2-dimensional hexagonal closed packed layer. In this layer many equal-sized triangular voids are present. Now first layer is placed horizontally. Now it is considered as a first layer for hexagonal close packing in 3 dimension. Let us label first layer as a layer. Now second layer are placed in depressions of the first layer, as the spheres of the second layer are aligned differently as compared to the first layer, so let us label second layer as B layer. That all triangular voids of the first layers are not covered by the spheres of the second layer, form octahedral voids and tetrahedral void. How octahedral void and tetrahedral void are formed. Consider first layer hexagonal close packed structure, and when second layer hexagonal close packed structure are placed on first layer, 2 types of voids are formed. First, octahedral void. Here in the animation you can see octahedral void, which is represented by letter O. Octahedral voids are formed by 3 sphere below, which is of first layer, and 3 sphere above, which is of second layer. Since octahedral voids are formed by 6 sphere, hence coordination NOF of octahedral void is 6. Here in the animation you can see tetrahedral void, which is represented by letter T. Tetrahedral voids are formed when 1 sphere from second layer cover the depression of first layer. Hence tetrahedral voids are 3 sphere below, which is of first layer, and 1 sphere above, which is of second layer. Since tetrahedral voids are formed by 4 spheres, hence coordination number of tetrahedral void is 4. Shape of octahedral and tetrahedral void. First octahedral void. Consider three sphere N, M and R represent lower layer, and sphere Q, O and P represent upper layer. While placing three sphere of one layer to three sphere of another layer, octahedral void are formed. Here octahedral void are represented as letter O. Octahedral voids are formed by joining all center of sphere N, M and R, and also center of sphere Q, O and P. Also join NQ and NO. Join PM and PR. Then join QM and OR. Thus octahedral hole has a shape of octahedron. Below image show the shape of octahedral hole. Tetrahedral void. When one sphere is placed on depression of the three sphere, a tetrahedral void are formed. Tetrahedral void are formed by joining all the center of sphere. This result in formation of tetrahedron shape structure of tetrahedral hole.
Formation of octahedral void and tetrahedral void. Now Aklesh sir will teach you how these voids are formed.
Now if I place like this is the hexagonal close packing in 2 dimension. Okay, now what I will do, I will take this HCP, hexagonal close packing structure, and I will place horizontally. Now this is the first layer for first layer of HCP in 3 dimension. So this is the first layer of HCP in 3 dimension. Now I will take another similar to the first layer, and I will place in such a way that the depression, you can see here there are lot of void space are there, here, all there are void space, and this void space are equal in size. Okay, this void space are equal in size. Now when I place this second layer on the voids of the first layer, then after placing the second layer on the voids of the first layer, now you can see there is a void space are formed. Okay, there are 2 type of void space are formed here. First I will show you this one. This void space is formed by 1, 2, 3 above, and below there is also 3 atoms, 1, 2 and below this 3. So this is a octahedral void. Octahedral void is formed by the 6 atoms, 3 atoms above and 3 atoms below. So this is the octahedral void. Now there is one more void space are formed, which is known as tetrahedral void. Here you can see there is a tetrahedral void. This tetrahedral void is formed by 4 atoms. How 4 atoms? See, 3 atoms, 1, 2, 3. The whole is surrounded by 3 atoms, and below there is only 1 atom, yellow color you can see. Okay, so this tetrahedral void is formed by 4 atoms, 1, 2, 3 and below 4. Tetrahedral void, and this is the octahedral void. So there is a alternate octahedral and tetrahedral voids are formed. This is the octahedral, tetrahedral, then again octahedral, then tetrahedral, octahedral, tetrahedral, octahedral. Okay, so there are 2 type of void space. One is octahedral, another is tetrahedral. So how the octahedral is formed? Suppose this is the first layer of the hexagonal close packing in 3 dimension, and if I place the second layer, this is the second layer, yellow one is the second layer, orange one is the first layer. Okay, so this is this space, you can see the empty space or void space. This is the octahedral void space. So how the octahedral is formed? Octahedral is formed by the total by 6 atoms and 3 atoms below and 3 atoms above. So a 6 atom. Therefore the coordination number of this octahedral void space is 6. Okay, now how the tetrahedral is formed? Suppose this is the first layer, okay, and if I placed another second layer exactly on the depression, okay, so the space which is formed, or you can see from the back side, the hole is created here, okay. This hole is known as tetrahedral void space. If you want to see in different way, what I will do, I will place like this, okay. So tetrahedral is formed by the 4 atoms, okay. You can see here 3 atoms above and 1 atoms below. The hole which is formed here is the tetrahedral void. So this tetrahedral void is formed by 4 atoms. Therefore the coordination number of the tetrahedral void space is 4.
Wow, what an explanation. Thank you Aklesh sir for the nice explanation. I will subscribe to Aklesh sir AV in YouTube.
Here first layer hexagonal close packing in 2 dimension is placed horizontally. Now it is considered as a first layer for hexagonal close packing in 3 dimension. Let us labeled first layer as a layer. Now second layer are placed in depressions of the first layer, as the spheres of the second layer are aligned differently as compared to the first layer, so let us labeled second layer as B layer. Here tetrahedral voids are formed by 3 sphere of above layer that is of second layer, and 1 sphere of lower layer that is of first layer. Now we will place third layer on tetrahedral void, so that all tetrahedral void is covered. After placing third layer over tetrahedral void, third layer arrangement match with arrangement of first layer. Since first layer is labeled as A layer, therefore third layer is also labeled as A layer. After placing fourth layer over tetrahedral void, fourth layer arrangement match with arrangement of second layer. Since second layer is labeled as B layer, therefore fourth layer is also labeled as B layer. The resulting pattern of the layers will be ABAB, type in 3 dimension. This ABAB type arrangement result in hexagonal close packed HCP structure. Consider A layer which is first layer, B layer which is second layer, again A layer which is of third layer. When second layer is placed on depression of first layer, tetrahedral void shape is formed, and when third layer is placed on tetrahedral void, resulting structure is hexagonal closed packed structure. Coordination number in HCP structure. Consider ABAB, type of hexagonal close packing structure. Here there is expanded view of AB type packing. Tetrahedral void space formed by first layer and second layer. Now third layer is placed on tetrahedral void space. Each sphere is surrounded by 12 neighboring spheres. 3 sphere above, 3 spheres below, 6 sphere of its own layer. Hence, coordination number equals 6 sphere on layer plus 3 lower layer plus 3 above layer. Therefore total coordination number equals 12. Hence, the coordination number of any sphere in HCP is 12.
AB type of arrangement in 3 dimension. So now you know that when I place the second layer on the first layer, there are 2 type of void space are formed. One is octahedral and another is tetrahedral. So there are, if I want to place the third layer of hexagonal close packing, so there are 2 types you can arrange the third layer. Either I can cover all the octahedral, or I can cover all the tetrahedral. You cannot cover both the void space simultaneously. Suppose if I place the third layer in such a way that all the tetrahedral, I am placing the third layer exactly on the tetrahedral void space. The tetrahedral void space. Okay, so when I place this on the tetrahedral, all the tetrahedral voids are covered, but no octahedral is not covered. Okay, so if I see the arrangement here, after placing the third layer is exactly matching the first layer. Suppose this, see, it is just exactly on the same line. Third layer atoms is exactly at the same line of the on the first layer atom. Okay, so if I consider this as A layer, then second layer is also not matching with the first layer. Therefore, I will consider the second layer as a B layer, and third layer is exactly similar to the first layer. Therefore, again I will say this is a layer. If I placed the third layer, this is also hexagonal close packing. Okay, so if I want to place, if I place the fourth layer on the depression of the first layer, the fourth layer is exactly in the same line of the second layer. So this will be the B layer. So how the arrangement is A B type of arrangement, and this is the hexagonal close packing structure. How the coordination number is determined? Take this atom. This atom is surrounded by the 6 atoms. Okay, and this atom touching the 3 atoms below, these 3 atoms. Okay, now I am placing C again. Here I am placing this. So this atom is surrounded by the 6 atoms, and below there is a 3 atoms, and above there is a 3 atoms. Okay, 12. How 12? 6 surrounded by, this atom is surrounded by 6 atoms, 3 atoms above, 3 atoms below. The total, there are 12 atoms is surrounded by this atom. Therefore, the coordination number of HCP is 12.
Magnesium has hexagonal crystal structure. This magnesium crystal structure is HCP structure. Happy Diwali! This zinc is hexagonal close packing structure. Remember, zinc is HCP crystal structure. Bye-bye. 3 Ventus cubic close packed structure. This cubic close packed structure is ABC ABCC type packing.
Now Aklesh sir will teach you about this CCP, hoping you will enjoy lecture.
Here first layer hexagonal close packing in 2 dimension is placed horizontally. Now it is considered as a first layer for hexagonal close packing in 3 dimension. Let us labeled first layer as a layer. Now second layer are placed in depressions of the first layer, as the spheres of the second layer are aligned differently as compared to the first layer, so let us labeled second layer as B layer. Now octahedral void are formed by 3 sphere above and 3 sphere below. Placing third layer on octahedral void. Now we will place hexagonal closed layer on second layer, so that all octahedral void are covered. After placing third hexagonal close packed layer on the second layer, so that sphere of the third layer cover all the octahedral voids. In such placing, the spheres of the third layer do not align with the spheres of the second layer. Here the spheres of the third layer also do not align with the spheres of the first layer. Since first layer is labeled as a layer, and second layer is labeled as B layer, third layer is labeled as C layer, as its arrangement is not same as A and B layer. Now when fourth layer is placed on octahedral void, then its arrangement matches with arrangement of first layer. So again fourth layer is labeled as a layer. In this way layer continues. This pattern of stacking hexagonal close packed layers is called ABC type packing. This ABC type of arrangement result in cubic close packed CCP. Consider expanded view of ABC type arrangement. Here when B layer is placed over A layer, octahedral voids are formed. When C layer are placed on octahedral layer, a cubic closed packed structure is formed. Each sphere is surrounded by 12 neighboring spheres. 3 sphere above, 3 spheres below, 6 sphere of its own layer. Hence, coordination number equals 6 sphere own layer plus 3 lower layer plus 3 above layer. Therefore total coordination number equals 12. Hence, the coordination number of any sphere in CCP or FCC is 12. Consider a layer B layer, C layer. Now B layer is placed on A layer. Octahedral void is formed. Now C layer will occupies all octahedral void. After placing fourth layer on third layer, this arrangement leads to formation of ABC type arrangement. This ABC type of arrangement results in face-centered cubic close packed FCC. Now cube is slightly tilted to 45 degree. Now both a layer is placed at opposite corner, which is A layer. First C layer sphere are placed. One sphere is placed at bottom corner inside the cube. 2 sphere is placed at adjacent face of cube. And 3 sphere placed diagonally in same upper face of cube. Now B layer sphere are placed. 1 sphere is placed at top corner front part of the cube. 2 sphere is placed at adjacent face of cube. And 3 sphere placed diagonally in same bottom face of cube. This result in face-centered cubic structure.
Number of voids per atom in hexagonal close packing and cubic close packing.
Calculate number of voids formed if we know number of atoms. Suppose there are n spheres in the crystal structure. Then the
number of octahedral void formed is equal to n. Here you can see if there is n sphere, then number of octahedral voids is also n. Number of tetrahedral void generated is equal to 2n. And if there is n sphere, then number of tetrahedral voids is also 2n. Here tetrahedral voids is double as number of sphere.
Packing efficiency in solid. Now we have to study how all sphere are packed.
Efficiency. The magnitude, that is strength of packing, is determined by packing efficiency, which gives a measure of how tightly particles are packed. If particle is loosely packed, then it has low packing efficiency. If particle is tightly packed, then it has high packing efficiency. Packing efficiency is the fraction of the total space occupied by the sphere's particles, or the percentage of the total space occupied by the sphere's particles. Here in the animation, sphere had occupied 74% of space in unit cell. Hence its packing efficiency is 74%. Packing efficiency is equal to volume occupied by particles in unit cell upon total volume of unit cell multiplied by 100.
Packing efficiency in simple cubic.
The packing efficiency of metal crystal in a simple cubic lattice.
packing efficiency in cubic crystal solid. 1.
In a unit cell, 8 atoms are present at 8 corners of unit cell. Since each corner atom is shared by 8 unit cells, its contribution to one unit cell is 1/8. Therefore, the number of atoms in one simple cubic unit cell is 8 multiplied by 1/8, which is equal to 1.
Cubic. Each corner atom contributes 1/8 part. There are 8 corners, so total contribution is 1 atom. 1 atom.
Step 2. Radius of sphere. In simple cubic unit cell, particles here spheric corners are at the corners. Here spheric corner in simple cubic unit cell. Touch each other at edges. Let R is the radius of atom and A is the edge length of unit cell. Hence, A equals 2R and R equals A by 2. Let this equation number 1. Step 3. Volume of sphere. Volume of sphere equals 4 by 3 pi R cubed. Equals 4 by 3 pi into A by 2 whole cube. Here you have to substitute a value of R from equation 1. Equals 4 pi A cubed divided by 3 into 8. Here a whole cube is A, and 2 cube is 8 here. Here 4 and 8 goes in 4 tables, so 4 1 times is 1 and 4 times 2 is 8. So volume of sphere is equals to pi A cubed divided by 3 into 2. Thus volume of sphere equals pi A cubed divided by 6. This is equation 2. Step 4. Total volume of particles. Here simple cubic unit cell contains only one particle. Here simple cubic unit cell contains 8 corners. Each corner contribute 1 by 8 particles. So all 8 particles together form one particle, that is one sphere. So simple cubic 1 particle to whole unit cell. Volume occupied by particles in unit cell is equal to pi A cube upon 6. Step 5. Packing efficiency. Packing fraction is equal to volume occupied by particle in unit cell divided by total volume of unit cell multiplied by 100. Now substitute the value. Volume occupied by particle is pi a cube divided by 6, and total volume of unit cell is a cube. Multiple by 100. After canceling a cube, we get pi by 6 multiplied by 100. This becomes 100 pi divided by 6. Now putting the value of pi as 3.142. We get packing efficiency equal to 52.36%. Therefore, percentage void space is equal to 100 minus 52.36, which is equal to 47.6%.
Packing efficiency of metal crystal in body-centered cubic lattice.
Derive packing efficiency of metal crystal in body-centered cubic lattice. 1. Number of atoms in body-centered unit cell.
Unit cell. There are 8 atoms at each corner positions and 1 atom at its body center. As each atom at the corner position contributes 1/8 to the unit cell, the contribution of those 8 corner atoms to the unit cell is 1 atom. The atom at the center of the unit cell is not shared by any other unit
cell, making total of 2 atom per body center.
Body-centered unit cell contain 1 whole atom in the center of unit cell. Remaining corner atom form 1 sphere. Body-centered unit cell contribute 2 atom per unit cell.
Step 2. Radius of sphere. In BCC unit cell, the particle at the center of the cube touches 2 corner particles along the diagonal of the cube.
In body-centered unit cell sphere with center C, that touches 2 corner of sphere with centra A and F.
To obtain radius of the particle,
Now we will apply Pythagoras' theorem to triangle EFD, and here angle E is right angle.
therefore FD square equals FE square plus ED square. Here FE equals ED equals A. Therefore, FD square is equal to a square plus a square. Therefore, FD square is equal to 2a square. Let this be equation 1.
Applying Pythagoras' theorem again to triangle AFD. For triangle AFD, angle ADF is equal to 90 degrees. So, using Pythagoras' theorem, AF square is equal to AD square plus FD square. Substituting the values of AD equal to AD and substituting from 1 we get AF square equals a square plus 2A square. So AF square becomes 3A square. Taking square root on both sides, AF is equal to root 3A. And this is our second result. Oh, there is a 3-sphere. All the sphere please come here. From the figure, we can see that the length of AF is equal to 4r. Let this be equation 3.
From equations 2 and 3, we get square root of 3 into a equals 4r. Rearranging the equation, we get r equals square root of 3 into a divided by 4. This is equation 4.
Step 3. Volume of sphere. Volume of a sphere is equal to 4 by 3 pi r cubed. Now, substituting r equals root 3a by 4. We get 4 by 3 pi multiplied by bracket root 3a divided by 4 whole cube. This becomes 4 pi multiplied by root 3 cubed times a cube, divided by 3 times 64. 4 and 64 goes in 4 tables, so after canceling, for it form 1 and by canceling 64 it goes in 16. And then cancel above and below 3, so it forms
3 pi a cube divided by 16.
This is equation 4.
Step 4. Total volume of particles. Here body-centered cubic unit cell contains only 2 particles. Here below animation you can see there are 1/8th atom at each corner and 1 atom at the center of unit cell. So total atom contributed by BCC unit cell is 2. Here both sphere is contributed by 1 unit cell. So volume occupied by particle in BCC unit cell is equal to 2 multiplied by root 3 pi a cube divided by 16.
Volume occupied by particle in BCC unit cell is equal to root 3 pi a cube by 8. Let this be equation 5th.
Step 5. Packing efficiency. Packing fraction is equal to volume occupied by particle in unit cell divided by total volume of unit cell multiplied by 100.
Square root of 3 multiplied by pi divided by 8 divided by a cube multiplied by 100. Here a cube above and a cube below get cancelled. Then square root of 3 pi by 8 multiplied by 100. Substituting value of root 3 as 1.732 and pi as 3.142. So, 1.732 multiplied by 3.142 multiplied by 100, divided by 8. After calculation, the result is approximately 68%. Therefore, percentage void space equals 100 minus 68, which is equal to 32%.
Packing efficiency of metal crystal in face-centered cubic lattice, or CCP, or HCP lattice.
Packing efficiency of metal crystal in face-centered cubic lattice, or CCP or HCP lattice.
Calculation of total No of atom present in face-centered unit cell. In below animation face-centered unit cell has 8 atoms are at the corner and 1 atom are present in each face of cube. In face-centered unit cell, each corner atom contribute 1/8 of atom to 1 unit cell. So when all 8 corner 1/8 atom are joined we get 1 atom. Total amount atom due to corner of unit cell is 1. Of each face of unit cell contain atom which contribute 1/2 of 1 unit cell. So when all 6 half atom of unit cell are joined we get 3 atoms. So total atom is equal to 1 atom due to corner and 3 atom due to face center. Total atom contributed by face-centered unit cell equals 4.
Face-centered unit contribute total 4 particles, 1 particles due to corner, and 3 particles due to face of unit cell. Bye-bye. Remaining concept Aklesh sir will teach you.
By applying Pythagoras' theorem to triangle ABC, angle ABC is equal to 90 degrees. Therefore, AC squared is equal to AB squared plus BC squared. Since AB is equal to A and BC is also equal to A, we get AC squared equals A squared plus A squared. So AC squared becomes 2A squared. Finally, AC is equal to square root of 2 times A.
From figure we can see that AC length is 4r. Let this be equation 2. From equation 1 and 2, square root of 2 into a is equal to 4r. So, r equals square root of 2a divided by 4. Now multiplying numerator and denominator by square root of 2. r equals square root of 2 into square root of 2 into a divided by 4 into square root of 2. This becomes r equals 2a divided by 4 root 2. Here 2 and 4 goes in 2 table therefore. Here 2 goes in 1 and 4 goes 2. So finally, r equals a divided by 2 root 2.
Step 3. Volume of sphere.
Volume of sphere is equal to 4 by 3 pi r cubed. Substituting r equals a divided by 2 root 2. Volume equals 4 by 3 pi into bracket a divided by 2 root 2 whole cube. Now simplifying. Volume equals 4 pi cubed divided by 3 into 8 into 2 root 2. After cancelling 4 and 8 which goes in 4 table we get. Finally, volume equals pi cubed divided by 12 root 2.
Let this be equation 4.
Step 4. Total volume of particles. Here face-centered cubic unit cell contains only 4 particle. 1 particle contributed by corner and 3 particles contributed by face of unit cell.
Volume occupied by particle in FCC unit cell is equal to, for x pi cubed divide by 12 root 2. Her 4 times 1 and 4 times 3 is 12. So finally, volume occupied by particle in FCC unit cell is equal to pi cubed divide by 3 root 2. Let this be equation 5. Step 5. Packing efficiency. Packing fraction is equal to volume occupied by particle in unit cell divided by total volume of unit cell multiplied by 100. Pi cubed divided by 3 root 2 multiplied by 100. A cube above and a cube below get cancel. This simplifies pi divided by 3 root 2 multiplied by 100. Now substituting values. Pi is approximately 1.732, and root 2 is approximately 1.414. So we get 1.732 multiplied by 100, divided by 3 multiplied by 1.414. Finally, the result comes out to be approximately 74%. Percentage void space equals 100 minus 74. Which is equal to 26%.
Number of particles in unit cell in X gram of metallic crystal. Let's learn this concept from Aklesh sir. Bye-bye.
Number of particles in unit cells in a metallic crystal. Let n be the number of particles present in one unit cell. In right side animation you see that different types of unit cells contain different numbers of atoms. In a simple cubic unit cell, n is equal to 1 atom per unit cell. In a body-centered cubic unit cell, n is equal to 2 atoms per unit cell. In a face-centered cubic unit cell, n is equal to 4 atoms per unit cell. Let a cube represent the volume of the unit cell. Let ρ, represented by the Greek letter ρ, be the density of the metal, and let capital M represent the molar mass of the metal.
Now what is molar mass?
Now consider sodium. We take 23 gram of sodium. In that there are 6.022 multiplied by 10 raised to 23 sodium atoms, which is Avogadro. This quantity is called 1 mole. This means that 23 grams of sodium contains 1 mole of particles. Thus, the molar mass of sodium is 23 grams per mole.
Let M represent mass of unit cell. Density, denoted by ρ, is equal to mass of unit cell divided by volume of unit cell. Mass of the unit cell can be written as number of particles into molar mass divided by Avogadro number whole divided by volume of unit cell. So, density is equal to n into m upon Na multiplied by a cube. Rearranging the formula, we get m is equal to ρ into Na into a cube divided by n.
Number of particles in x gram metal. Therefore molar mass, m, contains Na particles, that is Avogadro's particles. Let 23 gram of sodium atom contain 6.022 multiplied by 10 raised to 23. So here 23 gram is molar mass and this number represent Avogadro's number. So 23 gram of sodium metal contain 6.022 multiplied by 10 raised to 23 sodium atom. X gram of metal contain X grams multiplied by Avogadro's number, Na, divided by molar mass. Particles. Here an example. Now, if we take 115 grams of sodium then. So, number of atoms present in 115 is equal to 115, multiplied by 6.022 into 10 to the power 23 divided by 23. On solving by logarithm we get log 115 is 2.0607 plus log 6.022 is 0.7797. On addition it is 1.3617. Now log 23 is 2.0607. On subtracting with 1.3617, we get 1.4787. An antilog of 1.4787 is 30.1. Thus 115 grams sodium contain 30.1 x 10 raised to 23 atom.
Thus number of particle in x gram of metal is equal to xNa divided by capital M. The formula can be modified by substituting the value of molar mass m. The formula is number of particles in Xg equals xNa. Divide by rho a cube Na. Divided by n. After cancelling Na and above and below equation become number of particles in Xg equals xn divided by rho a cube.
Number of unit cell in x gram of metal. Trace. Number of unit cells in x gram of metal is equal to x divided by rho a cube. Chapter 1. Solid State. Part 4. Topic names are point defects, stoichiometric point defects, impurity defect, non-stoichiometric defects, electrical properties of solids, magnetic properties of solids.
To watch this topic, click on right side of video, click and subscribe, and leave a like button. Bye bye, meet you in next video.